This is a pre-built version of the application, so we can pick up data from one of three places, either from files or from the database or from hard-coded. So from file, we have the files here. From the database, we create the tables here with this class, and hard-coded, we have them hard-coded here. So for example, US cities or European cities, etc. And we put each one of those here. So either we add or remove here if we need to add groups of cities here. So if we open up this CSV file, we have the name of each city and their longitude and latitude coordinates. And here when we create the tables, for example, if we create the European cities table, we have the name and longitude, latitude and longitude coordinates, etc. And let's go ahead and run the application. Actually, before doing that, let's create the database. Do a refresh. So this database, and let's run the application. Maybe go with data coming from file. So we have those files, those options, and we'll go with Japanese cities. We have those cities, 2, 3, 4, 5. So 9 cities and their longitude and latitude coordinates. So maybe let's do brute force. And this is 9 factorial permutations. And now if we do genetic algorithm, so we end up with this distance, which is slightly higher than this one with brute force. So all of those are equivalent. And if we go with data coming from the database, we have those cities. And maybe let's go with European cities, and we have those 9 cities. So if we do brute force, we end up with 9 factorial permutations. And same thing if we do now maybe simulated annealing, we get this number, which is so 4805. So it's the same as brute force. And maybe hill climbing, let's do also here. And Let's go for hard-coded data and pick up US cities, and here we have 8 of them. So if we do brute force, and we have 8 factorial permutations, and now let's try nearest neighbors and ant colony optimization. Next, let's quickly go over the code. So this class represents a city identified by its longitude and latitude coordinates, and the Haversine formula is used for calculating distances between cities. And this class represents a route, and each route starts from one of the cities, visits each city once, and returns to the originating city. And it contains logic to calculate and return the total route distance. And this class creates and populates dataset tables, and each table contains a group of cities with their latitude and longitude coordinates, and we can add or remove tables as needed. And this class contains hard-coded groups of cities with their latitude and longitude coordinates, and we can add or remove groups as needed. And here cities data can be picked up from an SQL-Lite database, from file, or from hard-coded data. And we prompt the user for either table name, file name, or hard-coded data name. And extending classes implement the abstract method run algorithm, where a specific algorithm functionality is triggered, for example, hill climbing or genetic algorithm, etc. And this one is for simulated annealing, and the simulated annealing handler extends abstract handler. Same for the nearest neighbor. Have a nearest neighbor handler that extends abstract handler. Same for hill climbing, genetic algorithm, brute force, and ant colony optimization. So we have an ant colony optimization handler that extends abstract handler. So it triggers ant colony optimization functionality. And this handler triggers brute force functionality. And this one triggers genetic algorithm functionality. And if we look at the algorithms for example, brute force, so it systematically checks all possible candidate solutions until the correct one is found. And this one, ant colony optimization, is an algorithm inspired by how real ants find the shortest path to food, and key elements include artificial ants, pheromone trails, and evaporation. And this GA route is a route class used with genetic algorithm. And the population class is for a population of genetic algorithm candidate solutions. And here the genetic algorithm is inspired by biological evolution. It iteratively processes a population of candidate solutions using methods modeled on natural selection, crossover, and mutation to evolve and find the best possible solution. And hill climbing operates like climbing a foggy mountain. It constantly moves in the direction of the steepest immediate ascent until reaching a peak where no surrounding steps go higher. And nearest neighbor triggers nearest neighbor functionality. This one's a handler that extends abstract handler. And this one, the algorithm, it starts at an arbitrary city, repeatedly moves to the closest unvisited city, and finally returns to the starting city. And here we have a simulated annealing route. So used with simulated annealing algorithm. And this one works by progressively decreasing the temperature from an initial positive value to a set minimal. At each step, the algorithm randomly selects a solution close to the current solution we have, and it measures its quality and moves to it according to the temperature-dependent probabilities of selecting better or worse solutions. And we have this driver class. Actually, we have this utility class that we use with ant colony optimization. Atomic double. So the driver class drives the application, and the framework can use data coming from either one of three places. And it prompts the user for file, table, or hard-coded data source, and prompts the user for using either genetic algorithm, simulated annealing, or nearest neighbors, hill climbing, ant colony optimization, or brute force for finding the shortest traveling salesman problem route between cities. And here each city is identified by its latitude and longitude coordinates, and the Haversine formula is used for calculating a distance between two cities. Now the source code will be available for download. Also a members-only version, including step-by-step coding, will be available for viewing by channel members at the senior software engineer level and above.